Good morning, everyone. This is finally the last really theoretical lecture that we will need to do because it is really important to put all together, all our tools together in order to allow us to understand also what we will do in the application. And so let's start with the screen. So here you can see the screen, and we can start today with, as I said, the last talk about really the mathematical background that is around geotechnics. So we already talked yesterday regarding the stress inside the soil, as in other materials, and in soil, of course, stress are caused by external loads, and of course the volumetric weight inside the material itself. So soil, however, have a number of several properties that distinguish from other material, as we said. And firstly, we said that it is important to only transfer compressive normal stresses, non-tensile. So this is the first hypothesis that you should always remember regarding soils, and we will have time later to consider exactly what does it mean. Then the other important thing is that the shear stresses can only be transmitted if they are relatively small compared to normal stresses. Furthermore, it is characteristic of soil that part of the stresses is transferred by the water inside the pores. And this is a really, really important thing to be considered. And this chapter will consider exactly this thing. So water inside the pores. Because the normal stresses in soils usually are compressive, as we said, it is a standard practice to use a sign convention for stresses that is just opposite to what we use in classical mechanics. So the compressive stresses are positive and tensile stresses are negative. So the contrary of what generally you do. The stress tensor is denoted with sigma, and the sign convention for the stresses component is illustrated in this figure. The definition is that a stress component, when it acts in a positive coordinate direction on a plane, which is outward normal, has a negative coordinate direction, or when it acts in negative direction to a plane in positive direction. So you can see here the convention. This means that the sign of all stresses component is just opposite to the sign that you would have in most books of science, of engineering, so in applied mechanics, so be careful. It is also assumed that in indicating a stress component, sigma ij, yes, the first index denotes the plane on which the stress is acting, and the second index denotes the direction of the stress itself. This means, for instance, that the stress component, for example, sigma xy, indicate that the force in y direction acting upon a plane having its normal in the x direction is Fy as minus sigma xy ax, where ax denotes the area of the plane surface, the area that is crossed by the forces. The minus sign is indeed because of the sign convention of soil mechanics, assuming that the sign convention for forces is the same as in mechanics in general. So it's not easy in the beginning to have real ideas of the sign, but what we want to see is at this point the importance of pore pressure. So we said that soil is a porous material consisting of particles that together constitute the grain skeleton. In the pores of the grain skeleton, a fluid may be present. In general, this fluid is water. The pore pressure of all normal soil is such that the pores are mutually connected. So the water fills a space of every complex form, but it constitutes a single continuous body. In this water body, a pressure may be transmitted and the water may also flow through the pores. The pressure in the pore water is denoted as pore pressure. So, sorry if I already mentioned before, but we were talking about this pore pressure, so the water that is inside the pore. In a fluid at rest, no shear stress can be transmitted since this fluid is resting. This means that the pressure is the same in all directions. Of course, this is, it means that the element of soil is under equilibrium condition, for example, of this small triangular element, bounded by a vertical plane, an horizontal plane, and a sloping plane at an angle of 45 degrees. And if the pressure of the vertical plane at the right is P and the force on that plane is P per A, where A is the area of that plane. So, but because, as we said, there is no shear stress on lower horizontal plane, the horizontal force P per A must be equilibrated by a force component on a sloping plane, by this force. And at the same time, the vertical force must be in equilibrium with the vertical force of the lower horizontal plane of the element. So this have to be equilibrated by this, and this should be under equilibrium with this. Because the area of the element is also A, the pressure of that plate is P, small, equal to the pressure of the vertical plane. And using a little geometry, it can be shown that this pressure P acts at every plate through the same point. This is often denoted as Pascal principle. That is the one that you should have already encountered, known in physics or hydraulics. So this is the Pascal principle that it says that if there is no stress all around an element of soil, there is always P. If the water is at rest, the pressure in the water is determined by the location of the point considered with respect to the water surface. As shown by Stevin, the magnitude of the water pressure on the bottom of a container filled with water depends on the height of the column of water and the volumetric weight of the water, but not on the shape of the container. This is another important characteristic of physics. And the pressure at the bottom is P equal to D, that is the depth of the water level, and gamma V, where gamma V is, as we saw yesterday, the volumetric weight of the water, and the D is the depth below the water level. As we said, the total vertical force on the bottom is, of course, this volume per gamma, so gamma VWDA. Only in case of a container with a vertical slide, this is equal to the total weight of the water in the container. Stevin showed that the other type of container illustrated in this figure, the total force at the bottom is always gamma D. Gamma WDA is the same for all of these. This can be demonstrated by considering equilibrium of the water body, taking into account that the pressure in every point of the wall must always be perpendicular to the wall. This is, of course, a principle of physics that I don't have time to explain, but again, should be known. The container at the extreme right, this, for example, resembles a soil body, for example, like a body with a different layer of soil. With, of course, the pore space, and it can be concluded that the water in the soil satisfies the principle of staving of hydrostatics, provided that the water in the pore space form a continuous body. What I mean is that no matter what the form of the body is, the water always follow the hydrostatics, so the principle of Pascal and of staving. This is really important because okay, it's really important because our soils are very different each other. Instead, what about effective stresses? We considered, as you know, yesterday or the day before yesterday, the principle of Terzaghi. So now let's see what happened here when we have a stress and some shear stress may act. For the simple case, we have this C, isotropic normal stresses, a sort of the Cryer example that we have already done. And it is assumed that the magnitude of this stress acting in all directions is simply sigma. In the interior of the soil, for instance, at cross-section in the center, the stress is transmitted by the pore pressure P in the water and by the stresses in the particles. So it is important to remember that there is both the two components. One is the pore pressure, and the other one is the stress in or between the particles. It can be expected the stresses in the particle are generated partly by the concentrated force acting in the contact point among the particles, but also by the pressure in the water that surround the particles. And it can be expected that the deformation of the particle skeleton are almost completely determined by the concentrated forces in the contact points, since the structure can slide and roll between them in the contact points. So the pressure in the water results in an equal pressure in the grain. So this is the internal equilibrium in a soil. Again, the pressure in the water results in an equal pressure in the grain. So what it follows is that the pressure acts on the entire surface of the cross-section, and that by subtracting P from the total stress sigma, a measure from the contrast force is obtained. So we can also say that there are no contact forces between the particles, and a pressure P acts in the pore water. This same pressure P will also act in all the other particles because they are completely surrounded by the pore fluid. So the deformation in this case are the compression of the particles and the water that are both caused by the pressure P. So at this point, if we consider that, for example, quartz, that is a typical mineral of these particles, and water are very stiff materials, having an elastic moduli around 110 of the elastic modulus of steel. So that deformation in the case of them are very small because, as we said, they are very stiff. And so they can be neglected if compared with the large deformation that are usually observed in the soil, that is around 10 to the minus 3 and 10 to the minus 2. These considerations indicate that introducing the difference in the total stress sigma and the pore pressure, so the quantity sigma comma is denoted as the effective stresses, that is of course, Terzaghi principle. The effective stress is a measure for the concentrated forces acting in the contact points of a granular material. And in the case of no water, we can, of course, have the same, so sigma is equal to the effective stress. But most important is when the pressure is the same as the total stresses. In this case, instead, what we have is that the effective stress are 0. That means that in the contact points, there are no concentrated forces. It doesn't mean that the stresses in the grain is 0 in that case, because there will be always a stress in the particles that is equal to the pressure in the surrounding water. So the basic idea is that, as we said, that the deformation in the granular material are almost completely determined by the concentrated forces in the contact points of the grain that are at the same time moving each other with rolling and sliding. This is again introduced in historical time by Terzaghi with the following representation that is the same as we saw yesterday and also before. Sigma total is the sum of the effective stress and the pore pressure. So what about the effective stresses? Even though the equations are very simple and may seem almost trivial, the different expression may be found in some publication, especially relation of the form sigma plus NP, where N is porosity. So some books can give you this kind of things. The idea is that the pore pressure acts in the pores only, and so all the quantity N per P must be subtracted from the total stress to obtain the measure of the stresses in the particle skeleton. As the book here says, that it makes sense, and it can be also correct, but it ignores that soil deformation are not in the first place determined by the deformation of the individual particles. So we are not interested in all the pressure that is multiplied per n, but mainly by the changes in the geometry of the grain. So what we want to say here is that we are interested more in an average stress than the real stress that is acting in the pore. For this reason, the Terzaghi notion of the soil deformation are mainly determined by the contact force only, that, as we said, we can write this equation directly. Again, another important thing is that we can write this expression as we saw yesterday in the matrix notation, where delta is the delta of Kronecker or the unit matrix, and is 1 if E is like J, and 0 is they are different. Calculating the effective stresses in the soil is one of the main problems of soil mechanics, and effective stresses are important because they are responsible of the deformations. So again, what you want to remember is this all around this slide is fundamental that you remember this relationship. That is the Terzaghi relationship. Let me see. Yes. Okay. Then the concept of effective stress is so important for soil mechanics, as we said, that it gives careful consideration. It may be illuminating, for example, to note that the concept of effective stress is in agreement with the principle of Archimedes that say that there are forces all around a submerged body. And if we consider a volume of V with porosity n, the total weight of the particle is, of course, 1 minus n gamma p per v, in which gamma p is the volumetric weight of the particle material. If we want to say that is randomly, again, around 25.5 kilonewtons meter square, cubical, sorry, following Archimedes, the upward force underwater is equal to the weight of the water that is being displaced by the particle. So this 1 minus n that multiply gamma v per v is similar, is relative with this, but of course gamma w is the volumetric weight of the water that is around 10. So what it means is that there is a force that remain with by subtracting the first to the second expression, and we can consider, you can see here, this part minus this, which is what is transmitted to the bottom of the part of the soil on which the particle rests. And if the area of the volume is denoted by A and the height as h, I mean the volume is A per h, then we can write here, you can see the effective stress from the force, and subtracting, as we said, dividing per A, we can have simply that sigma first, sigma, the effective stress are, you can see 1 minus n that multiply gamma, the difference between the two gamma per h. This is why the shape of the container is not really important, and the quantity gamma p minus gamma v w is what we generally call the submerged volumetric weight. So when we have a soil that is submerged with water, we don't consider really the volumetric weight of the soil, so 26.5, but the difference, so 16.5. Following Tersaghi, the effective stresses must be determined as the difference of the total stress and the pore pressure. This is what we know. And at this point, if sigma is like gamma s per h, where gamma s is the volumetric weight of the soil, in this case, for example, 26.5, if the groundwater is at rest, the pore pressure can easily be determined as this. So the effective stress is gamma s 26.5 per h minus 10 per h, and this is what we can, how we can calculate sigma first from Tersaghi. But since we are in a saturated volumetric, in a saturated soil, we know from yesterday that we can define the volumetric weight in this manner by introducing n and 1 minus n, when n, of course, is the porosity. So at the end, we can also write this, putting inside this here, we can write sigma, comma, like 1 minus n that multiply gamma p per h minus 1 minus n gamma w per h, and at the end we obtain 1 minus n that multiply gamma p minus gamma v per h. That is, of course, identical of the expression that we obtain in advance. So, the Tersaghi principle is of effective stress appears to be in agreement with the principle of Archimedes, which is a fundamental principle of physics, as we said. It may be noticed that in the two methods, it has been assumed that the determining factor is the force transmitted between the particles and an eventual rigid surface, or the force transmittance between the grain. So at the end, this is another basic aspect of the concept of effective stress that cannot be concluded that Archimedes' principle automatically leads to the principle of effective stress. So they are both two phenomena, but they are not the same phenomenon. This is what we are talking here. Otherwise, when we consider the Terzaghi, that is more direct than the Archimedes principle, in general is more simple to be used. So this is why, in general, we use this value. And in particular, as we said, it's not necessary to put n to calculate the effective stresses. On the other side, the porosity is hidden inside the volumetric wave gamma S that is, as we said yesterday, no, the day before yesterday, a general value that define the entire soil. In fact, you can see here that N is present inside gamma S. So it's only modifying the position of N. The generalization of Terzaghi approach to more complicated cases, in case, for example, of non-saturated soil or flowing underground groundwater, is although very simple. So again, the pressure, even if the non-saturated soil, the total stress will be smaller because the soil is lighter, I mean, more deformable. On the other side, what is important is that the pore pressure remains always hydrostatic and the effective stress will be smaller even if there are many particles in the saturated case. But at the end, what I would like to say is that we can use the effective stress following from the total stress and then the total the pore pressure of the water for all possible loads as we are here. And so when we have these two stresses, we can determine the pore pressure and then the condition of the groundwater. Yes, we can start with an example. So this is a very simple case of a homogeneous layer, this of D depth, with you can see water here at the top, and of course we are interested in understand the pressure inside the soil. We can see that we have water here, and we can call the phreatic surface. At this point, it is possible to use, as we said, the Terzaghi principle. And if the atmospheric pressure is taking as 0, so P equals 0 at the phreatic surface, if there are also no capillarity effect in the soil, we can consider that this is what we generally call like the groundwater table. And at this point, if we consider, for example, the volumetric weight of the saturated soil as 20 kilonewton per meter cubic, the vertical normal stress in the soil now increases linearly with the depth. So you can see here that the total, that is this line, the total stress, sigma theta theta, is simply gamma per D. So D is this, and this coefficient is gamma. Since we are using this, of course, Terzaghi consideration, you can see here that the gamma V is instead this values, the blue one, and so the sigma comma zeta zeta is the difference between the total, all of this, and this blue one. So what I mean is that the effective stress is this triangle, red triangle. Let's see what's written. It is a consequence of a vertical equilibrium of a column of a stone of 8D, and it has been assumed that there are no shear stress on the vertical plane bounding the column in horizontal direction. That seems to be a reasonable assumption if the terrain, the soil, is homogeneous and very large with a single geological history. So if we consider all of this, the vertical stress at 10 meter, of course, is 20 kilonewton ratio m squared, that is 20 kPa. But since so it means that 10 per 20, right? Because the groundwater is at rest, the pressure in the water will be hydrostatic. So, as we said, P is gamma W per D. But since gamma W is the volumetric weight of the water, 10, it follows that at depth of 10 meters, the water will be 10 per 10, so 100 kilopascal. So it means that if this is 100 and this is 200, the difference, of course, is 100. So sigma, the effective stress, is, of course, gamma minus gamma V per D at each point along the depth of the soil. The vertical stiffness stress appear to be linear with depth, and this is a consequence of the linear distribution of the total stresses and the pore pressure, with both of them being zero at the same level, the soil surface. I would like now, I would like to show you other cases when things are a little bit more complicated than that. So, if we consider the equilibrium, you can see this picture, both in terms of total stress and effective stress, it can be found using the condition of vertical equilibrium only. The horizontal normal stresses remain, of course, at this case, undeterminate. But if we consider the horizontal stresses, if we consider, the horizontal equilibrium, the stresses cannot be determined, and a consideration of the equilibrium can be taken from this picture, that in particular define what we call the lateral stresses. That is one essential difficulties in mechanics, in soil mechanics, to be defined. So, if we want to understand what happened here in the horizontal stresses, we have to consider a little bit more parameters that will be later in the chapter. For now, we can consider this figure, where we can have, you can see here, what we call a capillary rise. In this case, we have a moving of the water from the soil to the container without the soil, and this movement is what we call capillarity rise. I don't want to enter more in this detail because this is what happens generally when we study the drain. Again, the zone that is above the phreatic level, this, of course, is considered the capillary zone. while the maximum height of the underwater above the phreatic level is denoted HC as the capillarity rise. So it means that all this water can move and goes inside the other container. What happened generally, for example, in sands, when you were children and you were playing in the sand. But I don't want to enter in very much detail. Why it is important here, instead of the definition of capillarity, to use for our application what capillarity is. So if we know that we have, for example, the possibility of the water that go up and down inside the soil, not only down but also up, we can study this picture. And we can see here that if we lower the phreatic level by 2 meters, with the possibility of capillarity rise, we can have an increase in the effective stresses. So if we have the same exercise case that we had here, but now we have the possibility of the water to move inside the 2 meters, the first 2 meters, you can see here that if we move the water here, you can see that these this triangle become smaller. So if this triangle becomes smaller, it means that since the external the total force, total pressures are the same, that the effective stresses are bigger. You can see here that the red zone is bigger. So let's read what is written. In practice, this will cause deformation, which will manifest in a subsidence of the ground level. So if the water come up and down inside the ground, and this can occur very often, especially in clays, the groundwater table is lowered. Lowering the water table to construct for example, a structure or a building within the building, it can lead to higher effective stresses to the soil, and therefore it can increase the settlements. So this may be accompanied by severe damage to the building and houses, especially if the settlements are not uniform. If the subsidence is uniform, there is less risk for damage of the structure founded on the soil of that area. We will go back when we will talk about soil structure interaction, of course, on this kind of problems. But for now, it is important to understand that if we lower this phreatic level that at the beginning is at 0, but if we lower, for example, a -2, you can evidently see that for capillarity, we have this the increase of the effective stress. Increase in the effective stress means that the stress between the particles increase, and this means that there will be more damage to the buildings. So in the first lesson, when somebody asked to me, this is the answer. If we remember that you asked me how I can build a structure, a new infrastructure near the buildings. This is the answer. If we don't know, if we don't do anything, this will be the consequence, so more damage to the existing buildings. But if we know this phenomenon, we can, of course, define the real design to avoid the damage. So let's see again what can happen. So if we lower the phreatic level also, can have some positive consequences. Let's see what happened. For instance, The increase of the effective stress at the soil surface make the soil much stiffer and stronger, so that heavier vehicles, for example tractors or other agricultural machines, can be supported. In case of a very high phreatic surface coinciding with the soil surface, for example, as we saw here, in this case, the effective stresses at the surface were zero, which means that there is no forces between the soil particles. Man, animal, machine then cannot find support of the soil and they may sink into it. The soil is called sonky and swampy. It seems natural that in such cases people will be motivated to lower the water level. So what happens if we lower the water level? What I said. This will result in some subsidence, and thus part of the effect of the lower groundwater table is lost. This can be restored by a further lowering of the water table, which in turn will lead to a further subsidence. In some places on the earth, the process had been almost catastrophic consequences, for example, in Venice and in Bangkok. The subsidence of Venice, for instance, was found to be caused by a large part by the production of ever-increasing amount of drinking water from the soil in the immediate vicinity of the city. So, lowering down the water create problems for the surrounding buildings. So this is what we need to know. And when the soil consists of a very coarse material, there will practically no capillarity. And in that case, lowering the phreatic level, for example, by 2 meters, will cause the top 2 meters of the soil to become dry, as here in this picture. And so it means that the upper 2 meters of the soil, they will become lighter. You see that there is no water here. A reasonably value for the dry volumetric water is, for example, gamma D. Remember, D, it means dry. 16 kilometers up to meter cubic. At a depth of 2 meters, the vertical effective stress now is, of course, 32 kilopascal. And at a depth of 10 meters, the effective stress is 112 kilopascal. It appears that in this case, the effective stress increased by 12, as we said, compared to the case of the water table coinciding with the ground surface. So if we compare with this, you can try on your own to do this calculation, to this graphic, to this diagram, and it appears, as we said, that there is an increase of 12%, and the distribution of total stresses, effective stress, and pore pressures is shown, as we said, in figure 5.5. Again, there will be a tendency for settlement of the soil, and we will consider a procedure for calculating the settlement as I said, when we will talk about soil-structure interaction. The subsidence of the soil can be also caused by an extraction of gas or oil from soil layers, and for example, the reservoirs containing oil generally are at a very substantial depth, and since the rocks are porous, the porosity is in general around 10–20%, it can remain filled with the gas or oil. And so for this reason, we can have, for example, several cases, for example, this in Groningen, that is a zone where you can see that the subsidence above the large gas reservoir was estimated to reach around 50 centimeters over a very large area. Honestly, it is the first the case that I ever write and listen around of 50 centimeters, half meter over a very so large area. But again, this is the point that this is what can happen with the water inside the soil. So again, there are several parts of the words where subsidence is really important, and definitely is done because of the presence of the vertical stresses. This example gives the idea how the total stress, the effective stress, and the pore stress can be determined on a horizontal plan in a soil consisting of a practical horizontal layers. In most cases, the best general procedure is that first the total stresses are determined. So first we determine the total stress, that is the most simple thing. Then we can define the total weight of the column, for example, the particles and the water, and then we can define the pore pressure from the hydraulic condition. When the groundwater is at rest, of course, is very simple to calculate. It's sufficient to determine the location of the phreatic surface, but if not, we have to define several procedures. But remaining in the case of phreatic surface, the pore pressure then are hydrostatic, starting from 0 at the level of the phreatic surface, and is linear with depth, as we said. So following definitely this scheme. So since they are so simple to be defined, it is very easy to use the Terzaghi principle, and we will see tomorrow in the exercises. When the soil is very fine, there should be, we have to consider the capillarity, because it can develop above the phreatic surface. And so at this point, we have to consider that water inside the soil is a very important peculiarity of soil mechanics. So let's see what happened with a final example in figure 5.6. It concerns a layer, the same layer of 10 meters thickness, but at this point we are carrying a surcharge, so a load of 50 kilopascal. At this point, the phreatic level is located at a depth of 5 meters. And it has been measured that in that soil there is a capillarity rise of 2 meters. So see how now it's complicated, because the volumetric weight of the soil when dry is, we said, 15 kilonewton per meter cubic, and when saturated is 20. Using this data, it can be concluded that at the top 3 meters of the soil, the top 3 meters, the soil is dry, of course, while the second part of the soil, from 7 to 10, it will be saturated by water. So the total pressure at the end of 10 meters will be 50, that is the 50 like if this is constant, plus 3 meters, this first 3 meters per 15, 16, that is this triangle, you can see, plus this triangle, that is 7 per 20, while 20 is because of saturation. So 15 is when it's dry per 3 meters, plus 20 per 7, when instead is saturated. And this means that these sigma zeta theta, it will be 238 kilopascal. At that depth, the pore pressure, of course, is this blue one, that is 5 per 5 per 10. 10 is gamma V, so it's 50. So coming to the Terzaghi principle, sigma the effective pressure, of course, at 10 meter are 238 minus 50. It means 188. The distribution of total stresses, effective stress and pore stresses are shown here. So I would like to leave some time a little bit. You can have on your own and then ask me some questions, because this can become a little bit more tricky than this and of course this. Okay, so let's see the application at this point of the Darcy law, because inside the soil we saw that there is also a flux of water. It's not only the water that is firm still, but there is the case of the Darcy law that we saw the previous lesson, and we know that in a porous medium the flow inside the water have to follow the equation of equilibrium, that is this three equation. You can see, of course, in vertical that the equilibrium need to have this term, that is the volumetric, the weight, the volumetric weight of water. And the quantity, again, as said, is the volumetric weight of the water, that is around 10 kilonewton per meter cubic. If there is no shear stress in the water, because again we are in a resting case, and is generally a good approximation, as we said, water is a viscous fluid, and shear stresses may occur in it, but only when the fluid is moving, and it has been assumed that the water is at rest. Furthermore, even when the fluid is moving, the shear stress is very small compared to the normal stress and the fluid pressure. So at this point, we can consider that the first equation defines that the pressure cannot change in the horizontal direction along x and along y. So the only equilibrium, the only direction where we can define the equilibrium is along the vertical direction. That requires the difference of the fluid pressure at the top and the bottom of a small element of course, soil, that is delta P. So delta P, if we consider here the equilibrium of water, we have that delta P is like minus gamma W per delta zeta. Delta zeta represents the height of the element. And if we consider, of course, that all these elements are infinite, so if we consider that delta zeta goes to 0, the third equation of the system can follow directly from this. You can see that we can put delta zeta here, and so we have delta P ratio delta zeta equal to minus gamma V. So what we want to say is that this Darcy law comes from a very intuitive considerations. So another important thing is that the volumetric weight, in general, we consider constant, but it's not. Sometimes is we can consider its variability, for example, with the temperature or with the density is discontinuous, for instance, in case of two different fluids with a sharp interface. But in general, for our consideration, we can consider that the weight is is continuous. So, for example, if we consider, as we said, that gamma W is constant, we can, of course, consider this and do the integration of this equation, and we obtain that P is equal, of course, minus gamma W per theta plus C, where C is the integration constant. What does it mean, this? This means that, of course, the fluid pressure is fully known with the integration constant, and not only that, we have, you can see here, the linear behavior of the pressure. So the pressure increases linearly with Z once we consider a constant. In the case of phreatic surface, for example, here, of course, the constant gives that in this point, the pore pressure is 0. So if we put that this point P is equal to 0, we can obtain C. That is, again, the integration constant. It is important to consider that we can have, for example, the same consideration if we put, you can see here, a tube inside the soil, and we can define the place, the level of the phreatic of the phreatic zone line with what we call a stand pipe. You can see here the stand pipe. That is a steel tube having a diameter, for example, of 2.5 centimeters with small holes in the bottom, so that the water can rise inside the pipe. Such a pipe can easily be installed into the ground by pressing on or eventually by hammering into the ground. And of course, the diameter is considered strong enough, big enough to calculate, to have the capillary effect, but also to be resistant inside the soil. And we can see with naked eye here, for example, that the for capillarity, as we considered before, the level rise up to the same level of the soil. So it is, of course, a simple method to measure the water level of a soil, but still one of the most important method that is very simple but generally used. For example, when you have a slope or heavy rains, this is a way to consider and to calculate the water surface. Of course, there are also measurements that can be more accurate with electronic measuring devices that measure the pressure in a small cell by a flexible membrane and a strained gas glue into the membrane. And of course, there are other methods, but the idea is that it is possible to measure the level of the water inside the soil with capillarity. This is the most important thing. So let's go a little bit further, and the hydrostatic distribution of pore pressure is valid when the underwater is at rest. So again, when the soil is at the pore distribution normal, we have no problem of capillarity. But when we have not hydrostatic condition, we have to think about several forces that are outside our element. So in this case, if I have forces outside the element, we cannot say that we are in hydrostatic condition anymore. And so you can see here the equation of equilibrium become delta P, which the derivation of P in X equal the component of the force in X, the component, the derivation of P along epsilon is equal to the force along epsilon, and of course we have to introduce F theta in this third, in the vertical direction. Again, the component of the force per unit of volume define definitely the difference between the previous case. And in particular, we have to consider what we already said, that the sign of this term have to be calculated by considering the equilibrium in one direction, for example, in figure 6.3. So both terms in the equation of equilibrium are positive, and so they can cancel. It is important at this time to consider that the equation of acceleration of a groundwater might also be taken into account. So it could be expressed by terms of rho A x, rho A epsilon, and rho A z, because, for example, we want to consider the gravity itself, so that represent the weight of the soil, of course. And at this point, we can consider that the velocity of flowing groundwater usually is of the order of magnitude of 1 meter per day, or smaller, 1 meter a day, or smaller. If such a velocity would be doubled in 1 hour, the acceleration, of course, will increase a little bit. It seems probable that the friction force between the particle and the water depend upon the velocity of the water, in particular such that the force will increase with increasing velocity and acting in opposite direction. It can also be expected that the friction force will be larger at the same velocity if the viscosity of the fluid is larger. From careful measurements, it has been established that the relation between the velocity and the friction force is linear, at least as a very good first approximation. At this point, so if the properties of the soil are similar all around in all the direction, we can consider the specific discharge, that is Qx, Qy, and Qz, that is a discharge per unit area. In a sort of sense, these correspond to the quantity that is Q ratio A. That is something like expressed, in volume per second. Volume per second per M2. That is a discharge per unit area. In the system, international system of unit, it is the dimension of a velocity. It also be noted that this is not the average velocity of the groundwater. Be careful, because that quantity quantify the discharge and has to be divided per the area of the pores only, not the area that is of the whole soil. because, of course, there is the porosity, that is the factor that reduces the scale. So the specific discharge is what we really want to know, is defined with the real velocity, that is V equal Q ratio N. In contrast with this first expression, which may be used for generally infinitively small elements here, within a single pore equation, we can define this equation, as we said. And in particular, we can consider the fact that we can introduce all these consideration inside this previous equation, and we can rewrite the discharge. Of course, you see, this was the component of the specific discharge. We can introduce delta P, delta X, delta P ratio delta X, delta P ratio delta Y, delta P ratio delta Z plus gamma V, that is this formulation inside the previous one, and we obtain the discharge, the relative discharge. This equation, and this is what I want to know from you, are the basic form of the Darcy law. They are named after the city engineer of the French town Dijon, who developed that law on a basing of an experiment in 1856. Darcy designed the public water works of the town of Dijon by producing water from the ground in the center of the town. He realized that this water could be supplied from the bigger area surrounding the town by flowing through the ground. So in order to assess the quantity that could be produced, he needed the permeability of the soil and therefore measure it. Yeah, then there is something else, but this equation are generally valid, but in the case also in the case of the volumetric weight can be not constant. And in civil engineer, many problems are concerned with a single fluid, for example, water, and the volumetric weight can be considered constant. Anyway, we can define what we call the groundwater head as theta plus P ratio gamma W. So if we introduce this inside the previous case, the previous formulation, we can obtain this equation, and at the end, the Darcy law, this, can be rewritten in this way. So essentially, we have that K represent the hydraulic conductivity. There is a C that is missing. The hydraulic conductivity. We can also call the coefficient of permeability, or in general, we just say the permeability. In fact, K small then should be denoted as the intrinsic permeability to avoid confusion. But when we generally talk about the Darcy law, that is what you see here, and that is what you should remember. So 6.10. We have here that K is the permeability. So what means that for Darcy law, the flux of water is proportional to the permeability along the various directions. So the flow along the X direction is proportional to the permeability in X, the other in Y, and the other in Z. Yeah, so if we want to do a very easy example, and then again, from tomorrow we will have some more cases, more exercises. At the end here of the presentation of today, I wanted to show at least an example. So for engineering practice, it is convenient to consider, for example, H, H as we consider Z plus P ratio gamma V. That is really simple to measure. You can see here instead, in fact, that if we introduce a pipe, as we said, we can split the part that is under pressure, under pore pressure, and the Z part that is, of course, inside the soil. So the concept of groundwater heat can be illustrated with, as I said, figure 6.5, and the water level is in the standpipe, measured with respect to a certain horizontal level, zeta 0. In the groundwater head H, yes, is the groundwater weight H in the point indicated by the open hand of the standpipe. When the standpipe is at rest, we can have, of course, a pressure at the end of the pipe that is P equal H minus Z per gamma P. So that, as we said before, H is Z plus P ratio gamma P. When the groundwater head is the same in every point of the soil water, of course, the groundwater will be at rest. Instead, in the case of non-constant head, the groundwater flow, of course, according to the equation of Darcy, will flow from location with a large head to location where the head is low. I mean, there is a flow that follows the vertical gravity. And of course, if there is, if the flow is not maintained by some external influence, for example, as I said, rainfalls or wells or something like that, of course, the water will tend towards a situation of constant head. So Darcy law can be written in this even simple case. Consider the direction of the flow, that in this case, of course, is the S direction, the Z direction. And we can write here this relationship with only the Z. So we can write Q equal minus K permeability dH ratio ds, where ds in this case is the hydraulic gradient E. You see here, dH ratio ds is what we can call the hydraulic gradient that represent the in the direction of the flow, of course, the increase of H ratio the unit of height. Of course, this gradient has a dimensionless, is a dimensionless quantity and indicate the slope of the phreatic surface. Is sort of an inclination. So if we have a friction between the water and the particle, we can introduce the friction inside, of course, the Darcy law. And since H is Z plus P ratio gamma V, we can express the groundwater head H, assuming then gamma V is constant, and we can write this relationship with the Darcy law. The force that water exerts on the soil skeleton is denoted by J, because the Newton third law, the principle of equality of action and reaction, is just the opposite of the force. So the vector quantity J is adopted in the C page force. It's just a vector to say that we are talking about a force instead of a J. So here we can also rewrite F force equal gamma per H point J. The C page force is especially important when considering local equilibrium in a soil, for instance, when investigating the condition of internal erosion, when some particle may become locally unstable because of a high flow rate. In the final slide, I will eliminate these two sentences because they are not really important for us. So let's see at this point the last example for today that is shown in figure, as we said, 5.6 is the same as we said before, but again, I recorded just to start from tomorrow from here. So please, at home, take a look again to this example, this, of course, and this example, and this example. And, of course, try to redo on your own, try to understand if you follow every point, if you understand what we have done here. Again, the fact that, for example, the pressure at the top is given by the 50 kPa, that is the load that is carrying on the surface. Then the fact that the water is at 3 meters. So the things that the consideration that the first part, the first 3 meters are dried, so we have to use gamma D, while the second part is saturated. So the first 3 parts we have to consider 16 and the second 20. And at the end, we use the consideration of Terzaghi, the Terzaghi principle, and we can see that when there is problem of fluctuation inside the water, the effective stress increase, and it means that we have to consider more damage inside the structures. So again, look again on this example. I will eliminate, of course, this slide as well. It was only to remind you. And so this is for today the lesson. I know that was a little long. Again, I want to, a little bit to record, do a little of synthetic things. We saw the stresses in the soil and also the importance of the pore pressures that follow the physics of the problems. So nothing new except for hydraulics. We introduce, we recall the Terzaghi problems, and we talk about the submerged volumetric weight. Then we did a first case with a very simple homogeneous layer, just to understand, just to explain the calculation of the Terzaghi principle. And then again, we started to do a little bit complex to the problem by introducing the capillarity. I show you how in the soil the capillarity, and you can read, the capillarity can move inside the soil. And here a first case of a 2 meter capillarity rise. Then we consider when the possibility of lowering the phreatic level, that you can see here is a different case. And finally, again, we put all together in this important, in my opinion, example, where you can consider both aspects of the problem. Last thing, important, consider what we said, that we don't consider in our models tensile stresses, but in this diagram, if we want to be honest, there is this part. This part is what I said, something that we neglect, but it exists. So it means that there is a part of the soil that entered in tensile. As I said, this is not really is important, but is not really considered in general as an approximation, and especially in this course, we don't follow particular attention because, as I said, the soil is a material that cannot have tensile forces. So, I think that for today is enough. So, thank you so much. And again, do the exercise, and we will meet tomorrow with all your questions at the beginning of the next lesson. There will be all examples. So thank you so much. Okay.